We start by updating the package index to ensure we get the latest version of OpenJDK 17. This is critical because Kafka 4.0 requires Java 17 or later. The output shows the package lists being refreshed from the Ubuntu repositories, confirming the system is ready for installation. Installing OpenJDK 17 provides the Java runtime Kafka needs. The -y flag skips confirmation prompts, making this step scriptable. The output confirms the package and its dependencies are installed, including the JDK and JRE. This is the foundation for running Kafka brokers. Verifying the Java version ensures the correct JDK is installed and available in the path. The output shows OpenJDK 17, which meets Kafka 4.0's requirements. This step is quick but essential. Kafka will fail to start if the wrong Java version is present. Downloading the official Kafka 4.0 tarball from Apache's Mirror ensures we get the latest stable release. The wget output shows the download progress and confirms the file size, which helps verify the integrity of the download. This tarball includes all Kafka binaries and scripts. Verifying the SHA 512 checksum ensures the downloaded file hasn't been corrupted or tampered with. The output should match the checksum published on Apache's website. This step is a security best practice when downloading software. Creating the opt/Kafka directory provides a standard location for Kafka installation. Using opt keeps the installation separate from system packages, making it easier to manage and upgrade. Extracting the tarball into/opt/Kafka with strip components equals 1 removes the top-level directory from the archive, placing Kafka files directly in /opt/Kafka. This simplifies paths when running Kafka scripts. Listing the contents of opt/Kafka/bin confirms the extraction was successful and shows key Kafka scripts. These scripts are the primary tools for interacting with the cluster. The output verifies the files are executable. Creating separate data directories for each broker ensures their logs and metadata don't interfere. Kafka uses these directories to store topic partitions and replication logs. The brace expansion creates all three directories in one command. Editing the first broker's configuration file defines its identity and behavior. This file controls critical settings like broker.id, which must be unique across the cluster, and log.drs pointing to the directory we created. Kafka 4.0 uses KRaft mode by default, so we don't need ZooKeeper configurations. The broker.id is especially important. If two brokers have the same ID, they'll conflict and cause data loss. We set listeners to PLAI in text /9092 for local connections and advertise.listeners to ensure producers and consumers can reach the broker. Configuring the second broker follows the same pattern as the first, but with unique broker.id and port. Here we set broker.id equals 2 and listeners equals PLAIN text //9093 to avoid port conflicts. The log.drs points to the second data directory. Keeping default.replication.factor equals 3 ensures new topics are created with 3 replicas, which is safe with 3 brokers. The advertise.listeners must match the port to ensure clients can connect. This broker will participate in the same cluster as broker 1. The third broker completes our cluster with broker.id equals 3 and listeners on port 9094. This broker will hold the third replica of each partition, enabling full fault tolerance. The log.drs points to the third data directory, ensuring its logs are isolated. With default.replication.factor equals 3, every partition will have 1 replica on each broker, so the cluster can survive the loss of any single broker without data loss. The advertise.listeners must match the port to ensure clients can discover and connect to this broker. Creating a systemd unit file for the first broker allows us to manage it as a service. This file specifies the user, working directory, and command to start the broker using our configuration. Using separate unit files for each broker ensures each runs in its own process and can be managed independently. The user equals Kafka line ensures the broker runs with limited privileges, improving security. The restart equals always directive ensures the broker restarts automatically if it crashes. The second broker's systemd unit file mirrors the first but points to its own configuration file. This ensures the broker starts with the correct broker.id, port, and data directory. Using separate unit files for each broker is a best practice because it allows independent lifecycle management. The after equals network.target directive ensures the broker starts only after the network is available, which is necessary for binding to its listener port. The restart equals always setting is particularly important for development clusters. The third broker's systemd unit file completes the trio, using its own configuration file. This setup allows all 3 brokers to run simultaneously on the same host, each managing its own set of partitions and replicas. The working directory equals opt/Kafka ensures the broker can find its scripts and libraries. The wanted by equals multi-user.targetLine ensures the broker starts automatically when the system boots, which is useful for development environments. Reloading the systemd daemon is necessary after creating or modifying unit files. This step ensures systemd recognizes the new Kafka Broker 1.service, Kafka Broker 2.service, and Kafka Broker 3.service files. Without this command, systemd would ignore the changes, and attempts to start the brokers would fail. Enabling and starting all three brokers in one command ensures they launch in parallel and persist across reboots. The now flag combines enable and start, saving time. The output shows symlinks being created, confirming the brokers will start automatically at boot. This step brings our Kafka cluster live. Running JPS lists all Java processes, which is the quickest way to verify the Kafka brokers are running. The output shows 3 Kafka processes, one for each broker, confirming they started successfully. JPS is preferred over PS for Java applications because it filters for JVM processes and shows their main class names. Checking the status of the first broker with systemctl provides detailed information about its health and resource usage. The output shows the broker is active and running, with its process ID and memory allocation. This confirms the broker started without errors and is managed by systemd. Creating a test topic with 3 partitions and replication factor 3 demonstrates the cluster's ability to handle partitioned and replicated data. The bootstrap server flag points to the first broker, which coordinates topic creation across the cluster. The output confirms the topic was created successfully. Describing the test topic shows how partitions and replicas are distributed across brokers. The output lists each partition, its leader, and the replicas, and in-sync replicas is. Here, each partition has 1 leader and 2 followers, with all replicas in sync. This confirms the cluster is functioning correctly. Starting the console producer allows us to send test messages to the test topic. The bootstrap server flag connects to the first broker, which routes messages to the appropriate partition leaders. The greater than prompt indicates the producer is ready for input. This demonstrates how producers interact with Kafka. Running the console consumer with from beginning reads all messages from the test topic. The bootstrap server flag connects to the first broker, which coordinates with partition leaders to fetch messages. The output shows the messages we sent earlier, confirming the producer and consumer are working correctly. Stopping the second broker simulates a broker failure, allowing us to observe how the cluster handles replication and leader election. This step is crucial for understanding Kafka's fault tolerance. When a broker goes down, its partitions replicas on other brokers take over as leaders. Describing the topic after stopping broker 2 shows how the cluster adapts to the failure. The ISR list for each partition no longer includes broker 2, indicating it's no longer available. The leader field for partitions previously led by broker 2 has shifted to brokers 1 or 3, demonstrating Kafka's automatic leader election. Restarting the second broker allows us to observe how it rejoins the cluster and catches up with missed messages. When a broker comes back online, it synchronizes with the leaders of its partitions to ensure it has the latest data. The cluster remains operational during this process. Describing the topic after broker 2 rejoins shows it has caught up and is now back in the ISR lists for all partitions. This confirms the broker successfully synchronized with the leaders and is fully operational again. The leader field may have shifted back to broker 2 for some partitions, demonstrating Kafka's ability to rebalance leadership. Stopping all 3 brokers gracefully shuts down the cluster, ensuring no data is lost. This step is necessary before cleaning up the data directories. The systemctl stop command sends a termination signal to each broker, allowing them to flush pending writes and close connections cleanly. Removing the data directories cleans up the cluster's state, ensuring a fresh start if we reinstall Kafka later. This step is destructive. It deletes all topic partitions, messages, and metadata stored by the brokers. The rm-rf command should be used with caution. Disabling the brokers ensures they won't start automatically on the next reboot. This step is important for cleaning up after a development cluster. The output shows the symlinks being removed, confirming the brokers are no longer enabled. This is the final step in tearing down the cluster.